Subscribe to the channel so you don't miss out on any of these videos. Have you ever wondered if the universe is hiding something far stranger than black holes? Something so mind-bending it could completely flip our understanding of the cosmos. Imagine this. What if those mysterious, dense points in space we call black holes aren't black holes at all? What if there's something entirely different, powered by an enigmatic force that we barely understand, dark energy? This isn't just science fiction. It's a legitimate hypothesis gaining traction among scientists. So buckle up, because what we're about to dive into will challenge everything you thought you knew about the universe. To set the stage, let's first talk about black holes, because they're the stars, pun intended, of this cosmic mystery. For decades, black holes have been the ultimate enigma in astrophysics. These regions of space are so dense that their gravity doesn't just pull in matter, it traps light itself. Anything that crosses the so-called event horizon, the point of no return, is gone forever, or so we think. Black holes have fascinated scientists and non-scientists alike, not just because of what we know about them, but because of how much we don't know. Even with all the incredible data from telescopes and simulations, black holes remain a paradox. They're described by Einstein's general relativity, but also seem to defy the very laws of physics as we understand them. But what if we've been misinterpreting the signs? Enter the idea of dark energy stars. This theory doesn't just tweak our understanding of black holes, it completely rewrites it. Instead of being infinitely dense points of matter, dark energy stars are hypothesized to be objects filled with, you guessed it, dark energy. And if that's true, the implications are staggering. To understand dark energy stars, we first need to break down dark energy itself. If you've been paying attention to recent discoveries about the universe, you'll know that dark energy is one of the most mysterious forces out there. It's the thing driving the accelerated expansion of the universe, acting as a sort of anti-gravity. Scientists estimate that dark energy makes up about 68% of the universe, yet we know almost nothing about what it is. We can't see it, we can't touch it, and we can't directly measure it. But its effects are everywhere, subtly shaping the cosmos on the largest scales. Now take this mysterious force and imagine it being concentrated in one place. That's the essence of the dark energy star hypothesis. Instead of a black hole collapsing into a singularity, a point where gravity is so strong that it warps space and time into oblivion, what if the collapsing star stopped short? What if, instead of forming a singularity, it created a core filled with dark energy? This is where things get interesting. Unlike a black hole, a dark energy star wouldn't have an event horizon. That means anything falling toward it wouldn't necessarily vanish forever. Instead, the matter could be stored or even repelled by the exotic properties of dark energy. This would explain some of the strange behaviors we observe around what we currently call black holes. For instance, the intense radiation emitted by material spiraling toward these objects could be caused by something entirely different than what we've assumed. Let's dive deeper into how this theory works. In a traditional black hole model, the event horizon forms because gravity becomes so strong that not even light can escape. Beyond this point, space and time effectively end. But in the dark energy star model, the immense gravitational pressure of a collapsing star doesn't lead to infinite density. Instead, it triggers a transformation. Dark energy begins to dominate, balancing out the collapse and creating a stable, albeit bizarre, object. Here's where the idea gets even more compelling. Dark energy stars could solve some of the biggest paradoxes in black hole physics. For example, the information paradox, a problem Stephen Hawking famously wrestled with, arises because black holes seem to destroy information about what falls into them, violating the rules of quantum mechanics. If black holes are actually dark energy stars, there might not be an event horizon to permanently trap that information. Instead, the matter and energy interacting with these objects could theoretically leave traces that we could one day detect. And let's not forget the singularity problem. A singularity is a point of infinite density where the known laws of physics break down. It's an uncomfortable concept for scientists because it suggests our understanding of the universe is incomplete. Dark energy stars eliminate the need for singularities altogether. By introducing dark energy into the equation, these objects could exist without defying the rules of physics, offering a much cleaner explanation for what's happening in the universe. But why hasn't this idea gained as much attention as traditional black holes? The answer lies in how challenging it is to test. Black holes, or what we think are black holes, are already incredibly difficult to study. They're so far away and so different from anything we encounter in everyday life that most of what we know comes from indirect observations. For now, dark energy stars remain a theoretical construct. But that doesn't mean they're not worth exploring. Imagine if future observations, perhaps from next-generation telescopes or advancements in quantum mechanics, could differentiate between black holes and dark energy stars. This would revolutionize astrophysics, opening up entirely new avenues of research. We'd be forced to rethink everything, from the nature of gravity to the fate of the universe itself. Even more tantalizing is the possibility that dark energy stars could explain other cosmic phenomena. Could they be linked to the mysterious flashes of energy we see in the form of gamma-ray bursts? Could they help us understand the role of dark energy in shaping galaxies and clusters of galaxies? The potential applications of this theory are endless. For now, we're left with more questions than answers. But that's the beauty of science. It thrives on curiosity and the drive to uncover the unknown. The concept of dark energy stars challenges us to think bigger, to question our assumptions, and to imagine possibilities that seem almost too strange to be true. And the next time you hear about a black hole, remember, it might not be what it seems. The universe has a way of surprising us, and dark energy stars could be one of its greatest surprises yet. This brings us to an important aspect of understanding the dark energy star hypothesis. What would it mean for our broader understanding of the cosmos? For decades, black holes have been considered the ultimate endgame for massive stars. They're where gravity wins, overwhelming every other force to create something so dense that space-time itself caves in. The very idea of black holes is rooted in Einstein's general relativity, which predicts their existence so convincingly that they've become a cornerstone of modern astrophysics. But what if this cornerstone is built on an incomplete picture of reality? Dark energy stars invite us to re-examine what happens during the collapse of massive stars. According to the traditional black hole model, when a star runs out of fuel, its core collapses under its own gravity, forming a singularity. But this process leaves room for some serious questions. For instance, why does the collapse have to result in infinite density? Why do the laws of physics seemingly break down at the event horizon? These are unresolved issues that have nagged at scientists for decades, and dark energy stars might hold the answers. Let's break this down further. If dark energy stars exist, they could be the result of a delicate balance between the forces of gravity and the properties of dark energy. As the collapsing star's density increases, it reaches a point where dark energy begins to dominate. Instead of forming an event horizon, the star stabilizes into a new state of matter and energy. This state would be governed by properties we're only beginning to understand. One of the most fascinating aspects of this theory is how it reframes our understanding of spacetime. Black holes are often described as tearing holes in the fabric of spacetime, creating singularities that essentially break the universe. Dark energy stars, on the other hand, might be less catastrophic. Instead of tearing spacetime apart, they could represent a form of cosmic equilibrium, a place where extreme conditions give rise to something entirely new. To explore this further, consider how dark energy already influences the universe on a massive scale. It's responsible for the accelerated expansion of space, meaning that the very fabric of the universe is stretching faster and faster over time. Now imagine this force being concentrated into a single object. The result would be something unlike anything we've ever encountered, an object that isn't just defined by gravity but also shaped by the mysterious, repulsive properties of dark energy. This opens up another intriguing possibility. Could dark energy stars be connected to the ultimate fate of the universe? Cosmologists have long debated what will happen to the universe in the distant future. Some theories suggest a big freeze, where the universe expands so much that stars burn out and everything becomes cold and dark. Others propose a big crunch, where gravity eventually reverses the expansion, pulling everything back into a singularity. But what if dark energy stars hint at a different outcome? If these objects are formed by the interaction of gravity and dark energy, they could provide clues about how these forces will evolve over time. For example, could dark energy stars act as reservoirs of dark energy, influencing the universe's expansion in ways we don't yet understand? Could they play a role in shaping the distribution of matter and energy across the cosmos? Another tantalizing question is whether dark energy stars could help explain the nature of dark energy itself. As it stands, dark energy is one of the biggest mysteries in physics. We know it exists because of its effects on the expansion of the universe, but we don't know what it is. If dark energy stars are real, studying them could offer a rare opportunity to investigate this elusive force up close, or at least as close as our instruments allow. This brings us to the observational challenges. Detecting a dark energy star would be incredibly difficult, especially since they might look very similar to black holes from a distance. Both would have intense gravitational fields, causing nearby matter to emit radiation as it spirals inward. However, there could be subtle differences in the behavior of this radiation. For example, dark energy stars might not emit the same patterns of X-rays or gamma rays that we associate with black holes. Additionally, the lack of an event horizon could mean that dark energy stars interact with their surroundings in unique ways. For instance, matter falling into a dark energy star might not disappear entirely but could instead be ejected or redistributed in ways that create distinct observational signatures. These differences could provide crucial evidence for or against the dark energy star hypothesis. One tool that could help in this quest is gravitational wave astronomy. Gravitational waves are ripples in space-time caused by massive objects moving or colliding. Black holes are known to produce gravitational waves during mergers, and the patterns of these waves provide valuable information about their properties. If dark energy stars exist, their gravitational wave signatures could differ from those of traditional black holes. Future observations could reveal these differences, offering a new way to test the theory. But let's take a step back and think about the broader implications of all this. If dark energy stars are real, they could represent an entirely new class of cosmic objects. They would challenge not just our understanding of black holes but also the fundamental principles of physics. The existence of dark energy stars would force us to rethink everything from the nature of gravity to the structure of space-time. And here's the kicker: if dark energy stars are out there, they might already be influencing the universe in ways we haven't even considered. They could be the engines driving the formation of galaxies, the seeds of cosmic structure, or even the key to understanding the universe's ultimate destiny. The idea of dark energy stars is a reminder of how little we truly know about the cosmos. It's a humbling thought, but also an exciting one. The universe is full of mysteries, and each new discovery brings us one step closer to understanding the bigger picture. Whether or not dark energy stars turn out to be real, the journey to uncover the truth will undoubtedly teach us more about the universe, and ourselves, than we ever imagined. The exploration of dark energy stars also underscores a larger trend in modern astrophysics: the growing realization that our current models might only scratch the surface of cosmic phenomena. Historically, theories about black holes emerged from equations and assumptions that seemed unassailable. But as technology improves and our ability to observe the universe becomes more sophisticated, cracks in these models begin to appear. For instance, the concept of a singularity, the infinitely dense core of a black hole, is problematic not only from a physical standpoint but also from a philosophical one. The very idea suggests a breakdown of all known laws of physics, creating an anything goes zone where the universe ceases to make sense. Dark energy stars offer an alternative that might restore a semblance of order to this chaotic picture. They suggest that instead of infinite density, there's a new state of matter and energy at play, something dynamic and comprehensible, though still deeply mysterious. This leads us to the role of quantum mechanics in this discussion. Black holes, as they are currently understood, sit at the uncomfortable intersection of general relativity and quantum theory. The two frameworks, one governing massive cosmic objects, the other governing the microscopic, don't play well together. In particular, the idea of a singularity creates a conflict between these two pillars of modern physics. Dark energy stars, on the other hand, might bridge this gap. By incorporating dark energy into the picture, they could provide a unified explanation that satisfies both quantum mechanics and relativity. This could open the door to a long-sought theory of everything, a framework that explains the universe at all scales. It's a tantalizing possibility, one that has driven countless hours of theoretical work and debate. Now, let's delve deeper into what dark energy stars might look like. One compelling idea is that they could appear as almost indistinguishable from black holes, at least from a distance. Their immense gravitational pull would create the same kind of shadow effect observed by the Event Horizon Telescope when it imaged the supermassive black hole at the center of the M87 galaxy. But up close, the differences would become apparent. For example, dark energy stars might not have the characteristic event horizon of a black hole. Instead, they could have a surface or boundary that interacts with matter in complex ways. This boundary could be composed of exotic materials or energy fields that defy our current understanding. Matter falling toward this surface might emit unique forms of radiation or behave in ways that challenge conventional expectations. The study of such objects could also provide new insights into the nature of dark energy itself. Despite accounting for roughly 70% of the universe's total energy, dark energy remains one of the greatest enigmas in science. Its effects are observable on a cosmic scale, but its properties at smaller scales are almost entirely unknown. If dark energy stars exist, they could act as laboratories for studying this mysterious force. By analyzing their behavior, we might uncover clues about what dark energy really is and how it influences the universe. Another fascinating question is whether dark energy stars could serve as gateways to new realms of physics. In many ways, black holes have been considered the ultimate test of our theories. They represent the most extreme environments in the universe, where gravity, density, and energy reach their limits. Dark energy stars could offer an even more nuanced challenge. Their unique properties might reveal new dimensions of physics that we've never encountered before, pushing the boundaries of human knowledge. Of course, all of this hinges on one critical factor: evidence. The dark energy star hypothesis is compelling, but it remains speculative without direct observational support. So, what would it take to prove, or disprove, this idea? The answer lies in the subtle details of how these objects interact with their surroundings. From gravitational wave patterns to X-ray emissions, every piece of data could provide a crucial piece of the puzzle. Let's consider gravitational waves as an example. When two black holes merge, they produce gravitational waves with distinct signatures. These waves have been detected by observatories like LIGO and Virgo, providing invaluable insights into the nature of black holes. If dark energy stars exist, their mergers might produce different patterns of gravitational waves, patterns that deviate from the standard black hole template. Detecting these deviations could provide strong evidence for the existence of dark energy stars. Similarly, the radiation emitted by matter falling into these objects could offer important clues. Traditional black holes produce characteristic X-rays and gamma rays as matter heats up and accelerates near the event horizon. Dark energy stars might produce similar emissions, but with subtle differences in energy levels, intensity, or duration. These differences could be detected by advanced telescopes, offering a potential way to distinguish between the two types of objects. But what about the implications for life in the universe? This might seem like a leap, but it's worth considering. If dark energy stars are real, they could play a role in shaping the conditions for life on a cosmic scale. For instance, their unique interactions with dark energy might influence the distribution of galaxies, stars, and planets. They could even affect the formation of habitable zones, creating environments where life might emerge. Moreover, the study of dark energy stars could inspire new technologies and methods for exploring the universe. Just as black hole research has driven advances in physics, engineering, and computation, the quest to understand dark energy stars could lead to breakthroughs in ways we can't yet imagine. From advanced telescopes to innovative simulations, the tools we develop could revolutionize our approach to space exploration. Let's address the philosophical implications. The idea of dark energy stars challenges us to rethink our place in the universe. If these objects exist, they represent a level of complexity and nuance that goes far beyond anything we've encountered before. They remind us that the universe is not only vast but also profoundly intricate, filled with phenomena that defy easy explanation. In many ways, the search for dark energy stars is a reflection of humanity's broader quest for knowledge. It's a journey driven by curiosity, imagination, and a deep-seated desire to understand the unknown. Whether or not we find definitive proof, the pursuit itself is a testament to the power of human ingenuity and the enduring mystery of the cosmos. This pursuit of dark energy stars also forces us to confront the limitations of our current scientific tools and methods. Despite the remarkable progress we've made in understanding the universe, there's an undeniable sense that we're still working with an incomplete toolkit. Observational astronomy, for example, relies heavily on electromagnetic radiation, light, radio waves, X-rays, and so on, to study distant objects. But dark energy stars, if they exist, might not conform to the traditional patterns of emission that we associate with black holes or other cosmic entities. This could make them extraordinarily difficult to detect. To tackle this, astronomers might need to develop new techniques or repurpose existing tools in creative ways. One promising avenue is the study of neutrinos, tiny, nearly massless particles that can pass through almost anything. Neutrinos are produced in some of the most extreme environments in the universe, including the interiors of stars and the aftermath of supernova explosions. If dark energy stars generate unique neutrino signatures, these could provide a crucial clue to their existence. Another potential method involves gravitational lensing, a phenomenon where massive objects bend the path of light from more distant sources. By carefully analyzing how light behaves as it passes near suspected dark energy stars, scientists could glean insights into their structure and properties. For instance, the absence of an event horizon or the presence of unusual energy distributions might become apparent through subtle distortions in the lensing effect. As we continue to refine these techniques, it's worth considering how the discovery of dark energy stars might reshape our understanding of cosmic evolution. Black holes are thought to play a critical role in the formation of galaxies, acting as anchors around which stars and gas coalesce. If what we've been calling black holes are actually dark energy stars, this would have profound implications for theories of galaxy formation. It could mean that dark energy, previously thought to be a force acting primarily on the largest scales of the universe, is also deeply embedded in the structure of galaxies themselves. This brings us to another intriguing possibility: the role of dark energy stars in cosmic expansion. Dark energy is currently understood as the driver of the universe's accelerating expansion, but its origins and mechanisms remain elusive. Could dark energy stars act as local reservoirs or sources of this mysterious force? If so, they might provide a missing link between the microcosmic and macrocosmic scales, uniting the dynamics of individual objects with the behavior of the universe as a whole. Such a connection would also have implications for the ultimate fate of the universe. Current models suggest that the cosmos might end in one of several ways: a big freeze, where expansion continues indefinitely, a big crunch, where it collapses back on itself, or a big rip, where dark energy tears everything apart. If dark energy stars are a significant factor in the cosmic equation, they could influence which of these scenarios comes to pass. For instance, their interactions with surrounding matter and energy might regulate the rate of expansion, acting as a kind of cosmic thermostat. But what if dark energy stars are not just passive participants in the universe's evolution? What if they have active roles to play, shaping their environments in ways we've yet to understand? Consider the possibility that these objects might act as engines for certain cosmic processes. Their unique properties could drive the formation of new stars, influence the distribution of dark matter, or even create the conditions for new forms of matter and energy to emerge. This leads to an even more speculative idea: could dark energy stars be connected to the multiverse? Some theories propose that our universe is just one of many, each with its own physical laws and constants. If dark energy stars exist, they might serve as gateways or transition points between these different universes. This idea, while highly speculative, opens up a realm of possibilities that challenges the very notion of reality as we understand it. Even without venturing into such speculative territory, the study of dark energy stars is already pushing the boundaries of what we know about spacetime itself. Traditional black holes are often described as holes in spacetime, regions where gravity becomes so strong that the fabric of the universe is warped beyond recognition. Dark energy stars, by contrast, might represent a different kind of spacetime anomaly, one that stabilizes rather than destabilizes the surrounding environment. This could have implications for our understanding of wormholes, time travel, and other exotic phenomena. At the same time, the search for dark energy stars raises important questions about the nature of scientific discovery. How do we balance the need for evidence with the drive to explore new ideas? What happens when a hypothesis challenges not just individual theories but the entire framework of a scientific field? These are the kinds of questions that keep scientists awake at night, and they're particularly relevant in the case of dark energy stars. The idea of dark energy stars also resonates with broader themes in human history and culture. Throughout the ages, we've been drawn to the unknown, whether it's the uncharted seas of Earth's surface or the vast expanses of the cosmos. Dark energy stars represent the latest frontier in this age-old quest, a mystery that invites us to look beyond what we think we know and imagine what might be possible. And this is where the human element comes in. The study of dark energy stars isn't just about equations and data. It's also about people, scientists, engineers, and thinkers who devote their lives to unraveling the universe's secrets. Their work reminds us that science is, at its core, a deeply human endeavor, one that reflects our innate curiosity and our capacity for wonder. As we look to the future, it's clear that the journey to understand dark energy stars is just beginning. New telescopes, such as the James Webb Space Telescope and next-generation gravitational wave detectors, promise to shed light on the most distant and mysterious corners of the cosmos. These tools, combined with advances in computational modeling and theoretical physics, could bring us closer to answering the question, are dark energy stars real? And if so, what do they mean for our understanding of the universe? The stakes are high, but so are the rewards. If dark energy stars exist, they could redefine not just our view of black holes but our entire conception of the cosmos. They could provide answers to some of the most profound questions in science while raising new ones that we can't yet imagine. In the end, the search for dark energy stars is a testament to the power of human curiosity, a reminder that no matter how much we learn, there will always be more to discover. The pursuit of dark energy stars represents a tantalizing step into the realm of the unknown, where our curiosity fuels exploration beyond the boundaries of what we currently understand. It challenges our long-held assumptions about black holes and the structure of the universe itself. But to truly grasp the significance of this concept, we need to reflect on the foundational principles of physics and cosmology that dark energy stars question, and the transformative impact their discovery could have on these fields. For decades, black holes have been regarded as the ultimate endpoint of massive stars, a point of no return where matter is compressed to an almost infinitesimal volume, creating a gravitational force so intense that even light cannot escape. They are defined by their event horizons, regions that mark the threshold beyond which escape is impossible. However, this traditional view leaves several questions unanswered. For instance, what happens to the information about matter that falls into a black hole? This dilemma, known as the black hole information paradox, has baffled physicists for years. Dark energy stars offer a potential resolution to this paradox by suggesting that these objects might not completely obliterate information. Instead, the matter and energy that fall into a dark energy star could interact with its interior dark energy content, creating phenomena we have yet to fully comprehend. This concept aligns with some interpretations of quantum mechanics, which argue that information cannot be completely destroyed. If dark energy stars preserve or transform information in ways we don't yet understand, it could offer a bridge between general relativity and quantum mechanics, two of the most significant but incompatible theories in modern physics. The implications of this are profound. General relativity governs the behavior of massive objects and the structure of spacetime, while quantum mechanics deals with the smallest scales of reality, such as particles and waves. A unified theory that combines these two frameworks, sometimes called quantum gravity, has long been a holy grail of physics. Dark energy stars might serve as natural laboratories for testing such theories, offering insights that could revolutionize our understanding of the universe. Moreover, the very nature of dark energy stars suggests that our perception of spacetime might be incomplete. In traditional models, spacetime is often visualized as a smooth, continuous fabric that can be warped by mass and energy. However, the presence of dark energy within these exotic objects hints at a more complex picture, one where spacetime itself might have additional layers or properties we've yet to uncover. For instance, dark energy stars could be manifestations of higher dimensional phenomena, as suggested by some interpretations of string theory. String theory posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. These strings operate in a multidimensional space, far beyond the three spatial dimensions and one time dimension we experience. If dark energy stars are connected to these higher dimensions, they could provide tangible evidence for string theory, a framework that has remained largely theoretical due to the lack of experimental confirmation. But what would this mean for our understanding of dark energy itself? Currently, dark energy is described as the force responsible for the accelerated expansion of the universe, making up about 68% of the total energy content of the cosmos. It is thought to be a uniform, diffuse phenomenon that acts on the largest scales. However, if dark energy stars exist, they suggest that this mysterious force might also have localized manifestations. In other words, dark energy might not just be a cosmic background force but also something that can cluster, concentrate, and interact with matter. This raises new questions about the distribution of dark energy throughout the universe. Are dark energy stars isolated anomalies, or are they part of a larger population of objects we have yet to detect? If the latter is true, their presence could significantly alter our models of cosmic structure and evolution. For example, dark energy stars might influence the formation of galaxies and galaxy clusters, acting as gravitational centers or stabilizing forces within these systems. On a more speculative note, dark energy stars could also be linked to the origin of the universe itself. The Big Bang Theory describes the universe as emerging from an initial singularity, a point of infinite density and temperature. But what if this singularity was not a black hole as traditionally envisioned but a form of dark energy star? Such a scenario would offer a new perspective on the conditions that gave rise to everything we know, potentially redefining the narrative of cosmic genesis. Another fascinating angle to consider is the potential for dark energy stars to harbor exotic forms of matter and energy. Traditional black holes are known to produce jets of high-energy particles, often seen in the form of quasars and other active galactic nuclei. If dark energy stars exhibit similar behavior, the mechanisms driving these emissions could be radically different. For instance, they might involve interactions between dark energy and normal matter, resulting in phenomena that challenge our current understanding of particle physics. Furthermore, dark energy stars could have implications for our search for extraterrestrial life. If these objects are fundamentally different from black holes, they might create environments with unique physical conditions. For example, the absence of an event horizon could allow certain forms of energy or matter to escape, potentially creating regions of space with unusual properties. These areas could, in turn, serve as habitats for life forms that are unlike anything we've encountered or imagined. Such speculations might seem far-fetched, but they highlight the broader significance of exploring the unknown. Every major scientific breakthrough, from the discovery of gravity to the realization that Earth orbits the Sun, began with questions that seemed implausible or absurd at the time. The study of dark energy stars is no different. It represents a leap into uncharted territory, guided by a combination of curiosity, skepticism, and imagination. Yet, the path forward is not without challenges. Detecting dark energy stars, if they exist, will require unprecedented levels of precision and creativity in our observational techniques. It will also demand collaboration across disciplines, from astrophysics and cosmology to quantum mechanics and particle physics. Such efforts are already underway, with international teams working on cutting-edge projects like the Event Horizon Telescope and the Laser Interferometer Space Antenna, LISA. These initiatives aim to probe the most extreme environments in the universe, from the edges of black holes to the ripples of spacetime itself. As these projects unfold, they will not only test the dark energy star hypothesis but also expand our understanding of the universe in ways we cannot yet predict. Whether or not dark energy stars exist, the search for them will undoubtedly yield new discoveries, forcing us to rethink our assumptions and refine our models. And in doing so, it will remind us of the power of science to illuminate the unknown, transforming mystery into understanding. The journey to understand dark energy stars is, in many ways, a microcosm of our broader quest to comprehend the cosmos. It is a story of questions without easy answers, of boundaries waiting to be pushed, and of the unrelenting human drive to explore. And while the answers may still lie hidden in the shadows, the very act of seeking them brings us closer to the light. The implications of dark energy stars are not just theoretical. They could redefine the tools and techniques we use to observe the universe. Traditional black holes are studied through phenomena like gravitational waves, X-ray emissions, and the bending of light around their immense gravitational fields. But if what we're observing are dark energy stars, then the signatures we interpret as evidence of black holes might need to be reanalyzed with fresh eyes. For instance, gravitational waves, the ripples in spacetime caused by massive objects accelerating, have been one of the most groundbreaking tools in astrophysics. Events like black hole mergers have been detected using instruments like LIGO and Virgo. If dark energy stars are responsible for some of these signals, the waveforms could contain subtle differences that point to their unique properties. This would require the development of new algorithms and models to decode these signals accurately. Similarly, the radiation emitted near what we perceive as black holes, such as X-rays from accretion disks, might also have different characteristics if the central object is a dark energy star. These disks form as matter spirals inward, heating up due to intense friction and emitting radiation across various wavelengths. If dark energy stars lack an event horizon, the interaction between the accretion disk and the star's surface, or its dark energy core, might produce distinctive emissions. Advanced telescopes like the James Webb Space Telescope could play a critical role in detecting and analyzing these variations. Moreover, the study of dark energy stars could shed light on another cosmic enigma: the nature of dark matter. Dark matter is an unseen substance that makes up about 27% of the universe's mass-energy content. Like dark energy, it remains one of the most perplexing mysteries in modern physics. If dark energy stars exist, they might interact with dark matter in ways that reveal clues about its composition and behavior. For example, the gravitational fields of dark energy stars could affect nearby dark matter, creating detectable distortions or concentrations. This interplay between dark energy and dark matter could also have profound implications for galaxy formation and evolution. Galaxies are thought to form around dark matter halos, regions of concentrated dark matter that provide the gravitational scaffolding for stars and gas to accumulate. If dark energy stars contribute to these processes, their influence might explain some of the irregularities and anomalies observed in galaxy structures. The potential connection between dark energy stars and dark matter also opens up new avenues for understanding cosmic voids, the vast, empty regions of space that make up most of the universe. These voids are surrounded by filaments of galaxies and dark matter, creating a structure often referred to as the cosmic web. If dark energy stars are part of this web, they could play a role in shaping the boundaries and dynamics of these voids, offering insights into the large-scale structure of the universe. But beyond the large-scale implications, dark energy stars also raise fascinating questions about the small-scale properties of matter and energy. For instance, if these objects contain dark energy cores, how does this energy interact with normal matter? Could it alter the properties of particles in its vicinity, such as their masses or charges? These interactions could have implications for fields like particle physics and quantum field theory, potentially revealing new forces or particles that extend beyond the Standard Model. The Standard Model of particle physics is a framework that describes the fundamental particles and forces in the universe, excluding gravity. While it has been incredibly successful in explaining a wide range of phenomena, it is incomplete. It does not account for dark energy, dark matter, or gravity at the quantum level. Dark energy stars could serve as a bridge between the macroscopic and microscopic worlds, providing clues that help unify these disparate realms. For instance, some theories suggest that dark energy stars might be related to hypothetical particles like axions or sterile neutrinos. Axions are ultralight particles proposed as a candidate for dark matter, while sterile neutrinos are a type of neutrino that interacts only through gravity. If dark energy stars produce or interact with these particles, their detection could provide direct evidence for these elusive components of the universe. This line of inquiry also has implications for the study of black hole thermodynamics, a field that explores the relationship between black holes and the laws of thermodynamics. Concepts like Hawking radiation, where black holes are thought to emit radiation due to quantum effects near the event horizon, could be reinterpreted in the context of dark energy stars. If these objects lack an event horizon, their radiation mechanisms might differ, potentially revealing new quantum phenomena. Furthermore, the concept of dark energy stars challenges our understanding of singularities, the points of infinite density at the centers of black holes. In classical physics, singularities are regarded as the ultimate breakdown of the laws of physics, a place where our equations no longer apply. However, if dark energy stars replace black holes, singularities might not exist in the way we currently envision. Instead, the extreme conditions inside these objects could be governed by entirely new physics, possibly involving quantum gravity or higher dimensional phenomena. The absence of singularities also raises philosophical questions about the nature of the universe. Singularities are often seen as paradoxical endpoints, places where time and space cease to exist. If dark energy stars eliminate the need for singularities, they could offer a more coherent and continuous model of the cosmos, one that avoids the conceptual pitfalls of infinite densities and zero-volume points. These philosophical implications extend to the broader question of what it means to know the universe. The study of dark energy stars reminds us that our current understanding is based on interpretations of limited data, filtered through the lens of human perception and technology. As our tools and theories evolve, so too does our picture of reality, revealing layers of complexity and nuance that challenge our assumptions and expand our horizons. In this sense, dark energy stars are more than just a theoretical curiosity. They are a symbol of the unknown, a reminder that the universe is far more intricate and mysterious than we can currently fathom. They invite us to question, to explore, and to imagine possibilities that lie beyond the boundaries of our current knowledge. As we continue to investigate these enigmatic objects, we are not just seeking answers to specific questions about black holes or dark energy. We are engaging in a deeper, more profound quest to understand our place in the cosmos, to uncover the fundamental principles that govern existence, and to embrace the wonder and mystery of the universe itself. The journey into understanding dark energy stars pushes us further into uncharted territory. These theoretical objects do more than challenge our existing models of black holes. They provoke deeper questions about the very framework of physics. At their core lies an opportunity to unify disparate elements of cosmology, quantum mechanics, and general relativity, fields that, despite their successes, remain frustratingly disconnected when applied to extreme conditions like those near black holes. One of the most profound implications of dark energy stars is their potential to address the so-called information paradox. Traditional black hole theory suggests that when matter falls into a black hole, all the information describing that matter is lost forever. This idea conflicts with the laws of quantum mechanics, which state that information cannot be destroyed. The paradox has haunted physicists for decades, leading to fierce debates and speculative solutions. Dark energy stars may offer a way out of this conundrum. If these objects lack an event horizon, then the matter falling into them might not be lost in the conventional sense. Instead, the dark energy core could store or even recycle this information, potentially allowing it to be retrieved or reinterpreted in some form. This would align with the principles of quantum mechanics while providing a new perspective on how information is preserved in the universe. But how might such information retrieval work? One intriguing possibility involves quantum entanglement, a phenomenon where particles become interconnected in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. If the structure of a dark energy star supports a network of entangled particles, it could enable information to be encoded and transmitted in ways that we are only beginning to understand. This idea ties into the emerging field of quantum information theory, which seeks to apply quantum principles to computing, communication, and cryptography. Another possibility is that the interaction between the dark energy star's core and its surrounding environment creates a feedback loop, where incoming matter and energy influence the star's properties in a measurable way. This feedback could produce detectable patterns or signals that encode information about the absorbed material. Advanced observational techniques, such as high-resolution spectroscopy or gravitational wave analysis, might reveal these patterns and provide a window into the star's internal processes. This line of reasoning also invites questions about time itself. In general relativity, the intense gravity of a black hole slows down time relative to an outside observer. Near the event horizon, time effectively comes to a standstill. But if dark energy stars lack event horizons, the time dilation effect might behave differently. Instead of freezing, time could stretch in unusual ways, creating a dynamic interplay between the star and its surroundings. This could have implications for the study of time loops, causality, and even the possibility of time travel. Time travel, while often relegated to science fiction, has a basis in theoretical physics, particularly in solutions to Einstein's field equations. Wormholes, for example, are hypothesized to connect distant points in spacetime, potentially allowing for shortcuts through the universe. If dark energy stars influence spacetime in novel ways, they could serve as natural laboratories for exploring these exotic phenomena. While the practicalities of time travel remain speculative at best, the theoretical groundwork laid by dark energy stars could offer new insights into the fabric of spacetime itself. The implications for cosmology are equally profound. If dark energy stars exist, they might represent a transitional phase in the life cycle of massive objects. Instead of collapsing into traditional black holes, some stars might evolve into these dark energy-filled entities, contributing to the universe's dark energy budget. This could help explain the accelerating expansion of the universe, a phenomenon attributed to dark energy but poorly understood in detail. The accelerating expansion of the universe is one of the most startling discoveries in modern cosmology. Observations of distant supernovae and the cosmic microwave background radiation have revealed that the universe is not just expanding but doing so at an increasing rate. Dark energy, thought to make up about 68% of the universe's energy content, is the driving force behind this acceleration. If dark energy stars contribute to this cosmic acceleration, they could provide a tangible link between local astrophysical processes and the large-scale dynamics of the universe. Furthermore, dark energy stars might play a role in shaping the evolution of galaxies and galaxy clusters. These massive objects could influence the motion of nearby stars and gas, creating gravitational effects that mimic those of traditional black holes. Over time, their interactions with surrounding matter could alter the distribution of dark matter and baryonic matter, leading to observable changes in galaxy structures. On a smaller scale, dark energy stars could also have implications for planetary systems. If such objects exist in binary systems with normal stars, their gravitational influence could affect the orbits and stability of planets, potentially creating environments conducive, or hostile, to life. Understanding these dynamics could expand the search for exoplanets and the conditions that support habitability. The philosophical and existential questions raised by dark energy stars are equally compelling. If these objects represent a new form of cosmic evolution, they challenge our assumptions about the life cycle of stars and the ultimate fate of the universe. Traditional models suggest that black holes eventually evaporate through Hawking radiation, leaving behind a cold, empty universe. But if dark energy stars replace black holes, they might offer a different narrative, one where energy and matter are recycled, creating a more dynamic and interconnected cosmos. Dark energy stars could symbolize a cosmic phoenix, rising from the ashes of collapsing stars to create something entirely new. They remind us that the universe is not a static, unchanging entity but a living, evolving system filled with surprises and possibilities. As we continue to explore the mysteries of dark energy stars, we are reminded of the power of human curiosity and imagination. These theoretical objects challenge us to think beyond the limits of our current knowledge, to question the assumptions that underpin our understanding of the universe, and to embrace the unknown with open minds and bold ideas. Whether or not dark energy stars ultimately prove to exist, the pursuit of their secrets will undoubtedly lead to new discoveries and insights that enrich our understanding of the cosmos. The notion of dark energy stars forces us to confront one of the deepest truths about science, that it is as much about the journey as the destination. Whether these entities are ever proven to exist or not, their exploration represents a bold step into the realms of theoretical physics and cosmology. To fully appreciate the scope of this possibility, we must delve even deeper into the mechanisms, implications, and controversies surrounding these fascinating objects. One of the most intriguing aspects of the dark energy star hypothesis lies in its ability to unify competing theories. For decades, physicists have sought to bridge the gap between general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles on the smallest scales. These two pillars of modern physics have resisted unification, creating a puzzle that remains unsolved. Dark energy stars offer a potential meeting point. Their internal structure, dominated by dark energy, might necessitate a quantum treatment of spacetime itself, forcing us to rethink the very fabric of reality. If the density of dark energy within these objects fluctuates at quantum scales, it could reveal new insights into how gravity behaves in extreme conditions. This could, in turn, provide clues to the elusive theory of quantum gravity, a holy grail in modern physics. Quantum gravity attempts to describe the gravitational force in terms of quantum mechanics. While many approaches have been proposed, such as string theory and loop quantum gravity, none have been conclusively proven. The study of dark energy stars might provide the experimental or observational data needed to validate one of these theories. For instance, the distribution of dark energy within such a star could resemble the behavior of strings or loops, offering indirect evidence for one of these frameworks. Moreover, the interaction between dark energy and the star's outer layers could produce unique observational signatures, such as unusual gravitational waves or electromagnetic radiation. Detecting these signals would require instruments of unprecedented sensitivity, but recent advancements in technology make this prospect less far-fetched. For example, the next generation of gravitational wave detectors, such as the Einstein telescope and LISA, laser interferometer space antenna, could potentially identify the subtle ripples produced by a dark energy star's dynamic processes. The observational challenges are immense, but they are not insurmountable. Dark energy stars would likely exist in regions of space with high densities of massive objects, such as the centers of galaxies or in binary systems with other stars. These environments are already the focus of intense study, thanks to their association with traditional black holes and other exotic phenomena. By refining our models and focusing our observations on specific regions, we could increase the chances of detecting a dark energy star. Another avenue for exploration involves the study of the cosmic microwave background (CMB) radiation, the faint glow of light left over from the Big Bang. This radiation carries information about the universe's early history and its subsequent evolution. If dark energy stars contribute to the universe's dark energy budget, their influence might leave subtle imprints on the CMB's structure. Advanced data analysis techniques, such as machine learning algorithms, could help identify these imprints and provide indirect evidence for the existence of dark energy stars. The potential for dark energy stars to reshape our understanding of cosmology cannot be overstated. They challenge the notion that black holes are the ultimate end state of stellar evolution, offering instead a vision of a universe where matter and energy are constantly transformed and repurposed. This has profound implications for our understanding of entropy, the arrow of time, and the ultimate fate of the cosmos. Entropy, a measure of disorder, is often associated with the second law of thermodynamics, which states that the total entropy of a closed system always increases over time. In the context of the universe, this law suggests a gradual progression toward a state of maximum entropy, often referred to as the heat death of the universe. However, if dark energy stars recycle matter and energy in unexpected ways, they could represent localized reductions in entropy, creating pockets of order within the broader march toward disorder. This raises questions about the arrow of time itself. Why does time flow in one direction? Is it an inherent property of the universe, or a consequence of our perception? Dark energy stars, with their unique interplay of gravity, quantum mechanics, and dark energy, could provide a testing ground for these questions. If their internal processes involve time-reversible phenomena, they might reveal new insights into the nature of time and its relationship to the universe's evolution. Philosophically, the existence of dark energy stars would force us to reconsider our place in the cosmos. Black holes, as traditionally understood, represent boundaries, places where the known laws of physics break down, leaving us unable to probe further. Dark energy stars, in contrast, suggest that these boundaries are not absolute. They offer a vision of a universe where even the most extreme conditions are governed by laws that we can, in principle, understand and explore. This shift in perspective has profound implications for humanity's quest for knowledge. It reinforces the idea that the universe is not a collection of isolated phenomena, but a deeply interconnected system where every element influences the others. By studying dark energy stars, we are not just exploring a specific type of celestial object. We are uncovering new layers of reality and expanding the boundaries of what is possible. Yet, as with any groundbreaking hypothesis, the concept of dark energy stars is not without its critics. Some physicists argue that the idea is overly speculative, relying on assumptions that have yet to be proven. They point out that the evidence for traditional black holes is overwhelming, and that dark energy stars must account for all these observations while providing additional explanatory power. This skepticism is a healthy and necessary part of the scientific process. It ensures that new ideas are rigorously tested and evaluated, preventing the field from being swayed by unverified claims. The challenge for proponents of dark energy stars is to develop models that make testable predictions, allowing the hypothesis to be evaluated on its merits. One way to address this challenge is through computer simulations. By modeling the behavior of dark energy stars under various conditions, researchers can predict their observational signatures and compare them to existing data. These simulations could also explore the transition from a collapsing star to a dark energy star, shedding light on the mechanisms that give rise to these exotic objects. The road ahead is uncertain, but it is also filled with promise. The study of dark energy stars represents a bold step into the unknown, a journey that challenges our assumptions and pushes the boundaries of what we know. It is a testament to the power of human curiosity and imagination, a reminder that the universe is far more complex and mysterious than we can currently comprehend. As we continue to explore the mysteries of dark energy stars, we are not just seeking answers to specific questions. We are participating in a grand tradition of inquiry that has defined humanity for millennia. Whether or not these objects exist, their study will undoubtedly lead to new discoveries and insights that enrich our understanding of the cosmos and our place within it. The pursuit of dark energy stars isn't just about exploring a theoretical alternative to black holes. It's about challenging the very frameworks that underpin our understanding of the universe. This exploration is a natural evolution of scientific inquiry, where each new hypothesis not only fills gaps in our knowledge but also opens doors to more profound questions. To continue this journey, we must consider the broader implications of dark energy stars for cosmology, particle physics, and the ultimate fate of the universe itself. One of the most compelling aspects of dark energy stars lies in their potential to address the mystery of dark energy itself. This enigmatic force, which accounts for roughly 68% of the universe's total energy, is believed to be responsible for the accelerated expansion of the cosmos. Despite its significant role, we know very little about what dark energy is or how it operates. If dark energy stars exist, they might serve as natural laboratories for studying this elusive phenomenon. The interior of a dark energy star is hypothesized to be dominated by a substance that mimics the properties of dark energy, pushing outward with negative pressure rather than pulling inward as gravity does. If this is the case, then understanding the microphysics of these objects could reveal whether dark energy is a fundamental property of spacetime, a new type of quantum field, or something even stranger. Observations of these stars could also provide clues about whether dark energy's influence changes over time, a question that has significant implications for the universe's long-term evolution. If dark energy is not a static, unchanging force but instead evolves with time or environmental conditions, this could alter our predictions for the fate of the universe. In the traditional view, dominated by the concept of black holes, the universe's future might end in a big freeze, where everything drifts apart and temperatures approach absolute zero. However, if dark energy stars recycle matter and energy in unexpected ways, they could introduce feedback mechanisms that slow or even counteract this progression. The presence of dark energy stars might also influence the distribution of galaxies and cosmic structures on a large scale. In standard cosmology, black holes play a critical role in shaping galaxies by anchoring them with their immense gravitational pull. If many of these so-called black holes are actually dark energy stars, their outward pressure could subtly reshape these dynamics, leading to different galactic formations and distributions. Observing these deviations could provide indirect evidence for the existence of dark energy stars. This hypothesis also invites us to rethink the singularity problem. Traditional black hole models suggest that their cores collapse into singularities, infinitely small, infinitely dense points where space-time curvature becomes infinite. Singularities pose a major challenge to physicists, as they signify the breakdown of general relativity and prevent further understanding. Dark energy stars, by contrast, eliminate the need for singularities. Instead, they propose that the extreme densities inside these objects stabilize due to the presence of dark energy, creating a finite, non-singular core. This stabilization has profound implications for our understanding of extreme physics. It suggests that nature avoids infinities, favoring mechanisms that prevent the complete collapse of matter. If this principle holds true, it might apply to other cosmic phenomena as well, offering new ways to approach long-standing puzzles in astrophysics and cosmology. Dark energy stars also provoke questions about the interaction between dark energy and regular matter. Could dark energy influence not just the interiors of stars but also their surroundings? For example, if dark energy stars emit any form of radiation, be it gravitational, electromagnetic, or something entirely unknown, this could interact with nearby matter in ways we have yet to observe or understand. Such interactions could produce unique phenomena, such as unusual jets of particles, strange light emissions, or unexpected patterns in the cosmic web. Another tantalizing question concerns the potential for these stars to harbor or create exotic particles. If dark energy stars involve conditions where spacetime itself fluctuates, they might give rise to particles that cannot exist under normal conditions. These particles could provide insights into the high-energy processes that occurred during the early universe, offering a window into its formative moments. Moreover, dark energy stars could have implications for our understanding of time. If their interiors involve fluctuations in spacetime, this might create regions where the flow of time behaves differently. Such time distortions could have profound consequences for objects orbiting these stars or even for the transmission of light and signals across cosmic distances. Detecting such effects would require incredibly precise measurements, but the payoff would be enormous, offering new insights into the nature of time itself. The exploration of dark energy stars also ties into broader questions about the anthropic principle and the fine-tuning of the universe. Why does the universe have the specific properties that allow life and complexity to emerge? If dark energy stars are a natural consequence of these properties, their existence might represent another layer of fine-tuning. Alternatively, they might suggest that the universe is even more diverse and complex than we currently understand, with room for phenomena far beyond what we can imagine. While the theoretical and observational challenges are daunting, the potential rewards are equally immense. The study of dark energy stars is not just about solving a specific mystery, it's about advancing our understanding of the universe in ways that could redefine our place within it. It's a reminder that science thrives on curiosity and bold ideas, even when those ideas challenge deeply held assumptions. The search for dark energy stars is as much about the journey as the destination. Whether or not they are ever confirmed, the process of exploring their possibility pushes the boundaries of human knowledge and creativity. It invites us to ask bigger questions, to dream bigger dreams, and to continue reaching for the stars, both literally and figuratively. As we delve deeper into the implications of dark energy stars, we must consider how their existence might alter our broader understanding of cosmic evolution. The concept of a universe filled with these exotic objects is profoundly different from one dominated solely by traditional black holes. Such a shift would challenge and refine many of the models we use to explain everything from galaxy formation to the ultimate fate of the cosmos. One particularly fascinating aspect is how dark energy stars could interact with their environment over time. Traditional black holes are often seen as isolated entities, regions of spacetime where nothing, not even light, can escape. However, if dark energy stars possess an internal structure that allows for the outward pressure of dark energy, they could act as dynamic participants in the cosmic landscape. For instance, their influence might extend far beyond their immediate vicinity, subtly shaping the behavior of nearby stars, gas clouds, and even entire galaxies. This idea introduces a new layer of complexity to the concept of accretion. In the case of black holes, accretion refers to the process by which matter spirals inward, heating up and releasing energy before disappearing past the event horizon. If dark energy stars lack a true event horizon and instead have a boundary where matter is repelled or transformed, the dynamics of accretion would look entirely different. Observing these differences could provide critical clues to distinguish dark energy stars from their black hole counterparts. For example, consider the energetic jets emitted by what are traditionally thought to be black holes, such as those in active galactic nuclei. These jets, which can stretch across millions of light years, are formed by the interaction of infalling matter with the black hole's intense gravitational and magnetic fields. If dark energy stars produce similar jets, the mechanics behind them would likely involve entirely new physics. Studying these jets in detail might reveal unique patterns, such as variations in their composition, speed, or frequency, that point to the presence of dark energy. Another intriguing possibility is that dark energy stars could act as cosmic recyclers. Traditional black holes are often viewed as the ultimate, dead ends, of matter and energy, trapping everything that crosses their event horizons. In contrast, if dark energy stars allow for some form of matter-energy conversion or re-emission, they might play an active role in redistributing material throughout the universe. This could have significant implications for galactic ecosystems, influencing the life cycles of stars and the distribution of elements necessary for planet formation and potentially life itself. This recycling mechanism might also explain certain anomalies in the universe's energy balance. Astronomers have long observed phenomena that seem to defy conventional explanations, such as regions of unexpected brightness or unexplained accelerations in galaxy clusters. If dark energy stars exist, their unique properties might account for some of these mysteries, offering a unifying framework that connects seemingly disparate observations. The impact of dark energy stars extends beyond astrophysics, reaching into the realm of particle physics and quantum mechanics. If the interiors of these stars are dominated by dark energy, this raises fundamental questions about the nature of this mysterious force. What particles or fields give rise to dark energy? How does it interact with normal matter and radiation? Could it be linked to other exotic phenomena, such as dark matter or the vacuum energy of quantum fields? Some theorists speculate that dark energy stars might contain regions where the laws of physics themselves break down, or at least differ significantly from those in the rest of the universe. These regions could serve as natural laboratories for exploring extreme conditions that are otherwise inaccessible, such as densities and temperatures far beyond those achievable in particle accelerators. Such conditions might reveal new particles or interactions that bridge the gap between general relativity and quantum mechanics, bringing us closer to a unified theory of everything. The study of dark energy stars also intersects with the search for extraterrestrial intelligence, SETI. If these objects are abundant in the universe and possess unique energy signatures, advanced civilizations might exploit them for energy harvesting or other purposes. Detecting unusual patterns in the vicinity of suspected dark energy stars, such as structured emissions or unexpected bursts of energy, could serve as a potential indicator of alien activity. While speculative, this line of thought adds yet another dimension to the importance of studying these objects. In addition to their scientific implications, dark energy stars also hold a unique place in the human imagination. They challenge us to rethink some of the most enduring concepts in science, such as the idea of an absolute end, represented by black holes. By proposing an alternative that replaces finality with transformation, dark energy stars offer a more dynamic and hopeful vision of the universe, one where endings give way to new beginnings. This perspective resonates with the philosophical idea that the universe is not a closed system but an ever-evolving tapestry of interconnected processes. If dark energy stars are real, they could embody this principle in a literal sense, serving as hubs of cosmic renewal and innovation. Such a view aligns with the broader trend in science toward understanding the universe as a dynamic, interconnected whole rather than a collection of isolated phenomena. However, proving the existence of dark energy stars remains a formidable challenge. Observationally, their properties may be difficult to distinguish from those of black holes, especially at great distances. Detecting subtle differences in light curves, gravitational wave patterns, or other phenomena will require advancements in technology and methodology. Theoretical work is also needed to refine the models and make specific, testable predictions that can guide observations. As we continue to probe the universe's deepest mysteries, the hypothesis of dark energy stars reminds us of the importance of keeping an open mind. History has shown that some of the most transformative discoveries in science began as radical ideas that challenged the status quo. Whether or not dark energy stars are ultimately confirmed, the process of exploring their possibility enriches our understanding of the cosmos and inspires us to keep asking bold questions. In the grand scheme of things, the search for dark energy stars is a testament to humanity's relentless curiosity and ingenuity. It represents our drive to understand the unknown, to push beyond the limits of current knowledge, and to imagine possibilities that transcend the ordinary. As we gaze into the night sky and wonder about the nature of the universe, the idea of dark energy stars serves as a powerful reminder that the answers we seek may be even stranger and more beautiful than we can currently comprehend. If we are to fully grasp the profound implications of dark energy stars, it is essential to consider how their potential existence might reshape our understanding of cosmic history. The evolution of the universe, as we know it, has been profoundly influenced by the formation and activity of black holes. These gravitational giants are thought to have played a key role in galaxy formation, regulating star formation, and driving the growth of large-scale cosmic structures. If what we call black holes are instead dark energy stars, then these processes might operate in ways we have yet to imagine. One key area of interest is the interplay between dark energy stars and the cosmic web, the vast, intricate network of galaxies, filaments, and voids that forms the large-scale structure of the universe. Traditional black holes are thought to anchor the centers of galaxies, providing the gravitational pull needed to hold them together. If dark energy stars fill this role instead, their unique properties could lead to subtle, yet significant, differences in how galaxies evolve over billions of years. For instance, the outward pressure exerted by dark energy within these stars might counterbalance their gravitational pull in unexpected ways. This could lead to variations in the distribution of stars and gas within galaxies, potentially explaining certain anomalies observed in galactic rotation curves and other phenomena often attributed to dark matter. Furthermore, if dark energy stars influence their surroundings differently than black holes, they might also affect the rate at which stars form, die, and recycle their material into new generations of celestial objects. Another fascinating implication of dark energy stars is their potential role in cosmic inflation, the rapid expansion of the universe that occurred in its earliest moments. Some theorists have proposed that dark energy stars could serve as microcosms of the inflationary process, providing insights into how dark energy might have driven the universe's exponential growth. By studying these objects, we might uncover clues about the mechanisms that set the stage for the universe we see today. But what about the future of the universe? If dark energy stars exist, they could play a pivotal role in determining how the cosmos evolves over the next billions or even trillions of years. In the traditional model, black holes are expected to dominate the end stages of the universe, growing ever larger as they consume matter and merge with one another. Over time, they would slowly evaporate through Hawking radiation, leaving behind a cold, dark expanse. However, if dark energy stars replace black holes in this narrative, the endgame could look very different. The constant outward push of dark energy might prevent these objects from collapsing further or evaporating entirely. Instead of fading into nothingness, dark energy stars might persist indefinitely, acting as reservoirs of energy and matter that continue to interact with their surroundings. This could lead to a more dynamic and complex cosmic end state, with pockets of activity persisting even as the universe approaches maximum entropy. This speculative scenario opens the door to a host of intriguing questions. Could dark energy stars serve as cradles for new universes, similar to the way black holes have been proposed as potential gateways to other dimensions? Might they act as cosmic seeds, sparking the formation of new structures or phenomena in an otherwise static universe? While these ideas remain firmly in the realm of hypothesis, they highlight the transformative potential of dark energy stars as a concept. The search for evidence of dark energy stars also invites us to rethink the tools and techniques we use to study the universe. Traditional methods of observing black holes, such as detecting their gravitational influence on nearby objects or analyzing the radiation emitted by infalling matter, may not be sufficient to distinguish them from dark energy stars. Instead, we may need to develop new approaches that focus on the subtle differences in their behavior and properties. For example, gravitational wave astronomy, a field still in its infancy, could provide valuable insights. The mergers of black holes produce distinct gravitational wave signals that can be detected by observatories like LIGO and Virgo. If dark energy stars merge in a different way, their gravitational wave signatures might reveal unique characteristics, such as variations in frequency or amplitude that deviate from predictions based on general relativity. Similarly, advancements in high-energy astrophysics could help us probe the interiors of dark energy stars. By studying the behavior of particles and radiation in the extreme environments near these objects, we might uncover evidence of the dark energy fields that define their structure. This would require not only more sensitive instruments but also new theoretical models that account for the interplay between dark energy and normal matter. Perhaps one of the most exciting aspects of the dark energy star hypothesis is its potential to bridge the gap between the macroscopic and microscopic realms of physics. Black holes are often seen as natural laboratories for testing the limits of general relativity and quantum mechanics, as their extreme conditions bring these two frameworks into direct conflict. Dark energy stars, with their unique properties, might provide an even richer testing ground for exploring the unification of these fundamental theories. For instance, the idea that dark energy stars lack a true singularity challenges the conventional view that spacetime must break down at extremely high densities. If these objects instead have a finite, structured core filled with dark energy, this could point to new physics that resolves the singularity problem. Such a discovery would have profound implications for our understanding of spacetime, gravity, and the fundamental nature of reality itself. The philosophical implications of dark energy stars are equally profound. These objects invite us to reconsider our place in the cosmos and the nature of the universe as a whole. If the boundaries of a dark energy star are not absolute but permeable, allowing for the exchange of matter and energy, they could symbolize a universe that is fundamentally interconnected and dynamic rather than static and isolated. In many ways, the study of dark energy stars exemplifies the spirit of scientific exploration. It challenges us to push the boundaries of what we know, to question our assumptions, and to imagine possibilities that lie beyond the horizon of current understanding. Whether or not these exotic objects are ultimately confirmed, the journey of investigating them enriches our knowledge and inspires us to continue seeking answers to the universe's deepest questions. As we stand on the cusp of new discoveries, the hypothesis of dark energy stars serves as a beacon of possibility. It invites us to look beyond the familiar and embrace the unknown, reminding us that the universe is far more wondrous and complex than we can yet comprehend. The idea of dark energy stars as a black hole alternative continues to spark debate and speculation in the scientific community. To truly understand the implications of these mysterious objects, we must delve deeper into their possible formation, behavior, and impact on our understanding of physics. One of the most compelling aspects of the dark energy star hypothesis is the possibility that these objects could form in a manner fundamentally different from traditional black holes. In standard astrophysical theory, black holes are thought to form when massive stars reach the end of their life cycle. After exhausting their nuclear fuel, these stars undergo a supernova explosion, leaving behind a dense core. If the core's mass exceeds a certain threshold, it collapses under its own gravity, forming a singularity surrounded by an event horizon. Dark energy stars, however, might arise from processes that incorporate not only gravitational collapse but also the unique properties of dark energy. During the final stages of a massive star's life, instead of collapsing into a singularity, the core could reach a state where dark energy is generated or becomes dominant. This would create a pressure that counteracts the star's gravitational pull, halting the collapse and stabilizing the object into a dark energy star. This idea aligns with theories suggesting that dark energy is not a uniform background field but can manifest locally under extreme conditions. If true, it would imply that dark energy stars represent a natural interplay between ordinary matter, and dark energy, three components that make up the fabric of the universe. The structure of a dark energy star would also be radically different from that of a black hole. While a black hole is defined by its event horizon, a boundary beyond which nothing can escape, a dark energy star might lack such a definitive edge. Instead, it could have a soft boundary, where matter and energy gradually transition into the dense, dark energy-dominated core. This gradation could explain certain phenomena that challenge the traditional black hole model, such as the apparent leakage of information or energy from what were once thought to be impenetrable boundaries. The absence of an event horizon would have profound implications for the information paradox, a long-standing problem in black hole physics. In the conventional view, information about matter that falls into a black hole is thought to be lost forever, violating fundamental principles of quantum mechanics. If dark energy stars replace black holes, the lack of a true event horizon means that information might not be lost but instead encoded in complex, subtle ways within the dark energy field. This would offer a potential resolution to one of the most perplexing puzzles in theoretical physics. Another area where dark energy stars could provide new insights is in the study of high-energy astrophysical phenomena. Black holes are known to power some of the universe's most energetic events, including gamma-ray bursts, quasars, and relativistic jets. If dark energy stars are responsible for these phenomena instead, it might change how we interpret their underlying mechanisms. For example, the intense radiation emitted by material falling into a black hole is thought to arise from the immense gravitational forces and frictional heating near the event horizon. In a dark energy star, these processes might operate differently. The presence of dark energy could create additional forces or interactions that modify the behavior of infalling matter, leading to variations in the observed radiation. By studying these emissions in greater detail, scientists could identify subtle differences that point to the existence of dark energy stars. The potential influence of dark energy stars on their surroundings extends beyond their immediate vicinity. These objects might play a role in shaping the distribution of matter on cosmic scales. The unique properties of dark energy could create long-range effects that alter the gravitational dynamics of galaxies and galaxy clusters. This could offer an alternative explanation for certain phenomena currently attributed to dark matter, such as the unexpected rotation curves of galaxies or the gravitational lensing effects seen in galaxy clusters. Furthermore, dark energy stars might hold clues to the nature of dark energy itself, a mystery that lies at the heart of modern cosmology. Despite its name, dark energy is not yet fully understood. It is generally described as a form of energy that permeates all of space and drives the accelerated expansion of the universe. However, its origin, composition, and behavior remain elusive. If dark energy stars exist, they could serve as natural laboratories for studying this enigmatic force. By examining how dark energy behaves in the extreme environments of these objects, scientists might uncover new properties or interactions that help explain its role in the universe. This could lead to breakthroughs in understanding not only dark energy but also the fundamental laws of physics. One particularly intriguing possibility is that dark energy stars could be linked to quantum gravity, a theoretical framework that seeks to unify general relativity and quantum mechanics. Traditional black holes are often cited as key to testing quantum gravity theories because they bring these two realms into direct conflict. Dark energy stars, with their unique properties, might provide an even richer testing ground for exploring the interplay between gravity and quantum effects. For instance, the idea that dark energy stars lack singularities could point to new physics that resolves the contradictions between general relativity and quantum mechanics. The finite density and structured nature of these objects suggests that spacetime might behave differently under extreme conditions, offering clues to the underlying fabric of the universe. As we consider the broader implications of dark energy stars, it is clear that their potential existence challenges many of our long-held assumptions about the cosmos. They invite us to revisit foundational concepts, explore new theoretical frameworks, and develop innovative methods of observation. Whether or not they are ultimately confirmed, the study of dark energy stars represents a bold step forward in our quest to understand the universe. The scientific journey toward uncovering the truth about dark energy stars is far from over. It will require collaboration across disciplines, from astrophysics and cosmology to particle physics and quantum mechanics. It will also demand the development of new technologies and observational techniques capable of probing the most extreme and elusive phenomena in the universe. Above all, the search for dark energy stars exemplifies the spirit of scientific inquiry, a willingness to question, to imagine, and to explore. It reminds us that the universe is a place of infinite wonder and mystery, always offering new horizons to discover and new challenges to overcome. The implications of dark energy stars stretch beyond astrophysics and into realms that could redefine how we view the universe itself. If these objects do exist, they could challenge the very foundation of our understanding of space, time, and energy. One of the most tantalizing aspects of the dark energy star hypothesis is how it reframes our interpretation of spacetime. Black holes, as predicted by Einstein's general theory of relativity, warp spacetime to such an extreme that nothing, not even light, can escape once it crosses the event horizon. But with dark energy stars, this warping might not reach the same finality. Instead of a singularity where the laws of physics break down, the core of a dark energy star might represent a different state of spacetime altogether, stabilized by the presence of dark energy. This stabilization could mean that spacetime inside these objects behaves in ways we've never seen before. For instance, the core of a dark energy star could act as a region where time slows drastically, or even where time flows differently compared to the external universe. Such an environment might have profound implications for the nature of causality and the interconnectedness of events across the cosmos. Another exciting implication is the potential connection between dark energy stars and cosmic inflation. Inflation theory suggests that in the earliest moments of the universe, an incredibly rapid expansion occurred, driven by an unknown force resembling dark energy. If dark energy stars harness a similar mechanism to stabilize themselves, they could be microcosmic analogues of the forces that shaped the entire universe in its infancy. Understanding these stars might provide clues to the origin of the cosmos itself, linking the smallest and largest scales of existence in a single framework. The possible existence of dark energy stars also raises questions about their detectability. Since they lack a traditional event horizon, their observational signatures would differ from those of black holes. Instead of the sharp cutoff associated with a black hole silhouette, a dark energy star might exhibit a more diffuse boundary where light and radiation interact with the dark energy field. This could result in unique patterns of emission, absorption, or scattering that astronomers might identify through advanced telescopes and imaging techniques. One area where this might become particularly relevant is in the study of gravitational waves. Black holes are known to produce gravitational waves when they merge, sending ripples through spacetime that can be detected by instruments like LIGO and Virgo. Dark energy stars, if they exist, would likely produce similar but distinguishable gravitational wave signals. These differences could help scientists differentiate between the two types of objects, providing critical evidence for or against the existence of dark energy stars. Additionally, the concept of dark energy stars could provide a new perspective on the enigmatic phenomenon of Hawking radiation. Proposed by Stephen Hawking, this theoretical radiation is thought to occur at the event horizons of black holes due to quantum effects. If dark energy stars replace black holes, they might produce a similar form of radiation, albeit through a different mechanism. The study of such emissions could shed light on the interaction between quantum mechanics and dark energy, opening a new window into the microcosmic underpinnings of the universe. Beyond their theoretical and observational implications, dark energy stars could also offer practical benefits for humanity's understanding of energy and matter. If these objects are stabilized by dark energy, they might hold the key to harnessing this elusive force. Dark energy is currently understood only in the context of cosmology, where it drives the accelerated expansion of the universe. However, if we can learn to manipulate or replicate the conditions inside a dark energy star, it could revolutionize energy production, enabling technologies far beyond our current capabilities. This potential for practical application underscores the importance of interdisciplinary research. To study dark energy stars effectively, scientists must bridge the gap between theoretical physics, astrophysics, and experimental technology. Advances in particle physics, such as those achieved through experiments at the Large Hadron Collider, could help us understand the behavior of matter and energy under extreme conditions. Similarly, breakthroughs in quantum computing and simulation might enable us to model the complex interactions within a dark energy star, providing insights that would be impossible to achieve through observation alone. The pursuit of knowledge about dark energy stars also has philosophical implications. These objects challenge our understanding of reality itself, forcing us to confront questions about the nature of existence, the limits of human comprehension, and the relationship between the observable universe and the unseen forces that shape it. In many ways, the study of dark energy stars is as much a journey of self-discovery as it is a scientific endeavor. It pushes us to expand our horizons, question our assumptions, and embrace the unknown. This philosophical dimension is particularly relevant when considering the role of dark energy stars in the broader context of cosmic evolution. If these objects exist, they might represent a natural endpoint for certain types of stellar evolution, offering an alternative to black holes and neutron stars. This could have far-reaching implications for the life cycles of galaxies, the distribution of matter in the universe, and even the eventual fate of the cosmos. For instance, dark energy stars might influence the way galaxies form and evolve. Their unique gravitational properties could affect the motion of stars and gas within galaxies, potentially altering the structure of spiral arms, galactic halos, or even the central bulges of galaxies. Over cosmic timescales, these effects might contribute to patterns and phenomena that we currently attribute to other forces or objects, such as dark matter. On an even grander scale, the existence of dark energy stars could impact theories about the ultimate destiny of the universe. If dark energy stars are a significant component of the cosmos, they might play a role in the so-called Big Rip scenario, where the accelerated expansion of the universe tears apart all matter. Alternatively, they could be linked to a cyclical model of the universe, where dark energy drives periods of expansion and contraction. Understanding these objects might help us refine our predictions about the future of the cosmos, offering new insights into the ultimate fate of everything we see. The study of dark energy stars is still in its infancy, but it represents one of the most exciting frontiers in modern astrophysics. As our observational capabilities improve and our theoretical models become more sophisticated, we may come closer to uncovering the truth about these mysterious objects. Whether they turn out to be real or remain a speculative hypothesis, they have already inspired new ways of thinking about the universe and our place within it. If dark energy stars do exist, they would force us to reimagine how the universe operates on both large and small scales. They would challenge the dominance of black holes in explaining extreme cosmic phenomena and provide an alternative lens through which to view gravity, space-time, and the elusive dark energy that permeates the cosmos. one crucial area of investigation for dark energy stars lies in their formation. Unlike black holes, which form from the gravitational collapse of massive stars, dark energy stars might require a completely different process. The conditions needed to generate such an exotic object could involve a combination of factors, such as specific quantum field interactions, extremely high energy densities, and unique gravitational effects. This raises questions about whether dark energy stars form naturally in the universe or require conditions we have not yet observed or understood. Some theories suggest that dark energy stars could form in regions of the universe where the density of dark energy is particularly high. These zones, perhaps located in the voids between galaxies, might allow for the stabilization of spacetime in a way that prevents the formation of a true singularity. Instead of collapsing into a black hole, matter and energy could become suspended in a delicate balance mediated by dark energy, creating a structure unlike anything else in the cosmos. Alternatively, dark energy stars could represent a stage in the life cycle of a black hole. Over time, the intense gravitational forces near the event horizon of a black hole might interact with quantum fields in a way that generates dark energy within the object. This transformation could cause the black hole to evolve into a dark energy star, altering its observable properties and reshaping its impact on its surrounding environment. If this hypothesis holds true, it would suggest that black holes and dark energy stars are not mutually exclusive but are instead interconnected stages of cosmic evolution. In exploring the nature of dark energy stars, scientists must also consider their potential role in the broader context of universal dynamics. For instance, these objects might act as reservoirs for dark energy, concentrating this mysterious force within their cores. If so, dark energy stars could influence the rate of cosmic expansion, acting as localized sources of repulsion that counteract the gravitational pull of nearby matter. This could help explain some of the inconsistencies in current models of dark energy distribution and its effects on the universe. Another intriguing possibility is that dark energy stars could serve as portals to different states of spacetime. While this idea ventures into speculative territory, it aligns with some interpretations of quantum gravity and string theory. The core of a dark energy star might contain regions where spacetime is highly curved or even connected to other dimensions. These regions could allow for phenomena such as wormholes or shortcuts through spacetime, offering a potential explanation for certain anomalies in astrophysical observations. This speculative nature of dark energy stars invites comparisons with other unconfirmed cosmic objects, such as white holes. While black holes are known to absorb matter and energy, white holes are theorized to do the opposite, expelling them into the universe. If dark energy stars exist, they might bridge the conceptual gap between these two extremes, functioning as objects that neither completely absorb nor completely repel matter and energy but instead exist in a state of balance. The study of dark energy stars is deeply interconnected with our understanding of quantum mechanics and general relativity. These two pillars of modern physics describe the universe at vastly different scales: the quantum realm of the very small and the cosmic realm of the very large. Dark energy stars could serve as a testing ground for unifying these theories, as they likely involve quantum effects occurring under extreme gravitational conditions. Such a unification is one of the greatest challenges in physics, and dark energy stars might hold the key to solving it. From a practical perspective, identifying and studying dark energy stars will require advances in technology and methodology. Current observational tools, such as the James Webb Space Telescope and gravitational wave detectors, are already pushing the boundaries of what we can observe. However, detecting the subtle differences between a black hole and a dark energy star will require even greater precision. New instruments capable of analyzing the behavior of light, particles, and gravitational waves near these objects will be essential. Moreover, simulations and theoretical models will play a crucial role in advancing our understanding of dark energy stars. By using supercomputers to model the extreme conditions near these objects, scientists can test various hypotheses and predict the observational signatures that would distinguish them from black holes. This iterative process of prediction and observation will be vital in determining whether dark energy stars are a real phenomenon or merely a theoretical construct. Public interest in topics like dark energy stars reflects humanity's innate curiosity about the universe. These objects challenge us to think beyond the familiar and consider the possibility that the cosmos is far stranger and more complex than we currently understand. They remind us that science is not just about answering questions but also about asking new ones, pushing the boundaries of knowledge, and embracing the unknown. In many ways, the search for dark energy stars is a metaphor for the human pursuit of understanding. Just as these objects might balance the forces of gravity and dark energy, our quest to understand them balances the known with the unknown, the observed with the speculative. Each new discovery brings us closer to answering fundamental questions about the universe, while also revealing new mysteries to explore. As we continue to study dark energy stars and their potential implications, we must remain open to the possibility that they might fundamentally change our understanding of reality. Whether they represent an alternative to black holes, a new state of matter, or a gateway to other dimensions, their discovery would mark a turning point in our exploration of the cosmos. And even if they remain hypothetical, the pursuit of this idea inspires new ways of thinking and fuels the curiosity that drives scientific progress. If dark energy stars do exist, their implications could extend far beyond the field of astrophysics, touching on areas like cosmology, particle physics, and even the philosophy of science. They challenge our preconceived notions about the universe and highlight the importance of questioning established ideas. By doing so, they remind us that scientific progress often comes not from clinging to what we think we know but from embracing the possibility of being wrong. One fascinating implication of dark energy stars is their potential impact on the fate of the universe. Current cosmological models suggest that the universe's expansion is accelerating, driven by dark energy. If dark energy stars are indeed reservoirs or generators of this mysterious force, they could influence how and where this expansion occurs. Instead of a uniform acceleration, there might be localized variations caused by the distribution of dark energy stars, leading to a more complex and dynamic picture of cosmic evolution. This possibility opens the door to questions about the long-term behavior of dark energy stars. Are they stable structures, or do they evolve over time? If they change, what drives this evolution, and what are the consequences for the universe? Some theories suggest that dark energy stars could eventually dissipate, releasing their stored dark energy into the cosmos. Others propose that they might merge or interact with other objects, creating phenomena that we have yet to observe or understand. These questions tie into another intriguing aspect of dark energy stars, their potential role in cosmic recycling. In the traditional view of black holes, matter and energy that cross the event horizon are lost to the observable universe. However, if dark energy stars replace black holes, this assumption might no longer hold. Instead of being lost, matter and energy could be transformed or repurposed within the dark energy star, contributing to the broader dynamics of the cosmos. This idea aligns with some interpretations of quantum mechanics, which emphasize the conservation and transformation of information. The concept of information plays a crucial role in the study of dark energy stars. In black hole physics, the information paradox is a long-standing problem that questions what happens to information about the matter that falls into a black hole. If dark energy stars replace black holes, they might offer a solution to this paradox. Instead of destroying information, these objects could encode it in a way that preserves it within the structure of space-time or in quantum fields. This possibility not only resolves a major theoretical issue but also suggests new ways of thinking about the relationship between matter, energy, and information. From a philosophical perspective, dark energy stars force us to reconsider our place in the universe. Black holes are often seen as cosmic endpoints, places where matter and energy reach their ultimate fate. In contrast, dark energy stars might represent a new beginning, a way for the universe to recycle and repurpose its components. This shift in perspective challenges the notion of finality and emphasizes the dynamic, ever-changing nature of the cosmos. It also raises questions about the potential for life and consciousness in a universe shaped by such exotic objects. Could dark energy stars support the conditions needed for life? At first glance, this idea seems far-fetched. These objects are likely surrounded by intense gravitational and electromagnetic forces, making them inhospitable by conventional standards. However, their unique properties might create pockets of stability, or regions where energy flows in unusual ways. In these niches, the building blocks of life could potentially arise, driven by processes that we have yet to imagine. While this idea is purely speculative, it underscores the importance of keeping an open mind when exploring the unknown. The search for dark energy stars also has practical implications for our understanding of space travel and technology. If these objects exist, they could serve as sources of energy, or as natural waypoints for navigating the universe. Their interaction with space-time might create regions where travel becomes easier or more efficient, similar to the concept of gravitational assists used in current space missions. While these possibilities are still in the realm of science fiction, they highlight the potential for dark energy stars to inspire new technologies and strategies for exploring the cosmos. As we continue to investigate dark energy stars, collaboration between different scientific disciplines will be essential. Astrophysicists, cosmologists, particle physicists, and quantum theorists all bring unique perspectives and tools to the table. By working together, they can develop more comprehensive models and experiments to test the existence and properties of these objects. This interdisciplinary approach reflects the broader trend in modern science, where solving complex problems requires input from multiple fields. The public's role in this exploration should not be underestimated. Interest in space mysteries, including dark energy stars, has the power to inspire new generations of scientists and engineers. Outreach efforts, documentaries, and educational programs can help demystify these concepts and encourage curiosity. By fostering a sense of wonder and excitement, we can ensure that the search for answers continues, driven by a collective desire to understand the universe. Ultimately, the study of dark energy stars is a testament to humanity's ability to think beyond the familiar and embrace the unknown. Whether these objects turn out to be real or remain a theoretical curiosity, their exploration pushes the boundaries of what we know and challenges us to imagine what might be. In doing so, they remind us that the universe is not just a collection of stars and galaxies but a vast, intricate web of mysteries waiting to be unraveled. The deeper we dive into the mystery of dark energy stars, the more we realize how interconnected this concept is with other pressing questions in cosmology and physics. For example, what role might these hypothetical objects play in the cosmic timeline? Could they have existed in the early universe, or are they phenomena that emerge only under specific conditions later in cosmic evolution? These questions are fundamental because understanding when and how dark energy stars could form would provide insights into the universe's structure and history. One area worth exploring is the connection between dark energy stars and the Big Bang. The universe's origin was a moment of extreme energy density, followed by rapid expansion. In the aftermath, various types of matter and energy formed, including the seeds of black holes. However, if dark energy stars exist, could they also have emerged during this period? It's possible that the unique balance of forces required to create a dark energy star might have been more common in the chaotic, high-energy environment of the early universe. If this is the case, some of the primordial black holes, theorized to have formed shortly after the Big Bang, might actually be dark energy stars in disguise. This hypothesis could have profound implications for how we understand dark matter and dark energy. Both are essential components of the universe, yet their exact nature remains elusive. If dark energy stars are real, they might offer a bridge between these two mysteries. For instance, the concentration of dark energy within these objects could explain some of the gravitational effects attributed to dark matter. At the same time, their interactions with surrounding matter and energy could shed light on the behavior and distribution of dark energy in the universe. Furthermore, the existence of dark energy stars could reshape our understanding of galaxy formation and evolution. Black holes are thought to play a central role in the growth of galaxies, anchoring their centers and influencing the behavior of surrounding stars and gas. If some of these black holes are actually dark energy stars, their influence might be quite different. Instead of acting solely as gravitational anchors, they could also emit or modulate dark energy, affecting the dynamics of galaxy formation in ways we have yet to comprehend. This could explain certain anomalies in galactic behavior that current models struggle to address. The observational evidence for dark energy stars remains a significant challenge. Current technology can detect the presence of black holes through their gravitational influence, and the effects they have on nearby matter, such as the emission of X-rays from accreting material. However, distinguishing a dark energy star from a black hole might require far more precise measurements. One promising avenue is the study of gravitational waves. Black holes produce characteristic gravitational wave signatures when they merge, and dark energy stars, if they exist, might produce slightly different patterns. Detecting these differences would require highly sensitive instruments, but advancements in gravitational wave astronomy could make this possible in the near future. Another potential method of detection involves studying the behavior of light near the event horizon, or in the case of dark energy stars, near the boundary that resembles an event horizon. If dark energy stars lack a true singularity, the light bending around them might follow a subtly different pattern compared to black holes. This difference could manifest in the way these objects distort the light from background stars, a phenomenon known as gravitational lensing. Advanced telescopes and imaging techniques might one day reveal these subtle distinctions. Theoretical physics also plays a crucial role in exploring the plausibility of dark energy stars. By developing mathematical models that describe the behavior of dark energy under extreme conditions, scientists can predict the properties and observational signatures of these objects. For instance, some theories suggest that dark energy stars might emit a faint, unique form of radiation due to interactions between quantum fields and their outer layers. Detecting such radiation would be a groundbreaking discovery, providing direct evidence for their existence. As we investigate dark energy stars, we must also grapple with their implications for fundamental physics. These objects challenge the notion of singularities, which are central to our understanding of black holes. Singularities represent points where our current theories of physics break down, with infinite density and zero volume. Dark energy stars, by contrast, propose a finite, stable structure where dark energy counteracts gravitational collapse. This idea not only sidesteps the problem of singularities but also offers a potential path toward reconciling general relativity with quantum mechanics. The implications for quantum gravity are particularly intriguing. If dark energy stars represent a stable equilibrium between gravity and quantum effects, they could provide a natural laboratory for studying how these forces interact. This could help bridge the gap between general relativity, which describes gravity, and quantum mechanics, which governs the behavior of particles at microscopic scales. A successful theory of quantum gravity would revolutionize our understanding of the universe, and dark energy stars might be a key piece of this puzzle. Philosophically, the concept of dark energy stars forces us to confront the limitations of human understanding. For decades, black holes have been a cornerstone of astrophysics, with countless observations and theories built around them. The idea that these objects might not exist in the way we think they do challenges our confidence in established knowledge. It's a humbling reminder that science is a dynamic process, where even the most well-supported ideas can be revised or replaced as new evidence emerges. Moreover, the study of dark energy stars highlights the interplay between theory and observation in scientific discovery. While the concept of these objects is rooted in theoretical physics, proving their existence, or lack thereof, requires innovative observational techniques. This interplay underscores the importance of maintaining a balance between imagination and evidence, pushing the boundaries of what we know while grounding our ideas in observable reality. Public engagement with this topic is also essential. Concepts like dark energy stars captivate the imagination and spark curiosity about the universe. By sharing these ideas through accessible and engaging formats, scientists and educators can inspire the next generation of thinkers and explorers. Whether through documentaries, podcasts, or educational outreach, the story of dark energy stars has the potential to ignite a sense of wonder and a thirst for knowledge. The search for dark energy stars is about more than just understanding a specific type of object. It's about exploring the unknown, challenging our assumptions, and expanding the horizons of human knowledge. Whether these objects turn out to be real or remain a theoretical construct, their exploration embodies the spirit of scientific inquiry, a relentless pursuit of truth, guided by curiosity and driven by the belief that the universe still holds countless mysteries waiting to be uncovered. The exploration of dark energy stars opens up a fascinating frontier in the quest to understand the universe's most enigmatic phenomena. The journey to uncover their secrets does not merely challenge our understanding of black holes, it also redefines how we interpret the fundamental forces that govern the cosmos. As we delve deeper into the theoretical frameworks and the potential observational evidence, we are forced to rethink the boundaries of what is possible in nature. One of the most compelling aspects of the dark energy star hypothesis is its potential to address long-standing inconsistencies in our understanding of black holes. Traditional black hole models are deeply rooted in Einstein's theory of general relativity, which describes how massive objects curve spacetime. According to this theory, a sufficiently massive and compact object will form an event horizon, a point beyond which nothing, not even light, can escape. This process leads to the formation of a singularity, a region of infinite density where the known laws of physics break down. However, singularities have always been a troubling concept for physicists. They represent a failure of our current theories to fully describe reality. The equations of general relativity predict infinite density and zero volume at the core of a black hole, but these conditions are physically nonsensical. This paradox indicates the need for a new theory, one that unites general relativity with quantum mechanics. Dark energy stars offer an alternative to singularities by proposing that dark energy prevents complete gravitational collapse, creating a stable, finite structure instead of an infinitely dense point. This idea is not just a mathematical convenience, it has profound implications for our understanding of spacetime and gravity. If dark energy stars exist, they could provide a natural resolution to the singularity problem, offering a more complete picture of extreme gravitational phenomena. Furthermore, the interaction between dark energy and matter within these objects could shed light on the nature of dark energy itself, a force that currently defies explanation despite accounting for approximately 68% of the universe's total energy. The study of dark energy stars also intersects with other groundbreaking theories in physics. For example, the idea of a quantum vacuum plays a crucial role in understanding these objects. The quantum vacuum is not empty but teeming with virtual particles that constantly pop in and out of existence. This sea of fluctuating energy could interact with the outer layers of a dark energy star, creating unique radiation signatures that might be detectable with advanced instruments. Another intriguing connection lies in the field of holography. The holographic principle suggests that the information contained within a three-dimensional volume of space can be encoded on its two-dimensional boundary. This concept has been applied to black holes, where the event horizon is thought to store all the information about the matter and energy that falls into them. If dark energy stars replace black holes, they might also exhibit holographic properties, but with crucial differences that could provide new insights into the nature of spacetime and information. The implications for cosmology are equally profound. Dark energy stars could play a role in explaining the accelerated expansion of the universe. Current models attribute this phenomenon to a mysterious force known as dark energy, which counteracts gravity on cosmic scales. If dark energy stars are reservoirs of this force, their distribution and interactions could influence the universe's large-scale structure and expansion rate. This connection could help unify our understanding of dark energy at both local and cosmic scales. From an observational standpoint, identifying dark energy stars requires innovative approaches and cutting-edge technology. One promising avenue is the study of accretion disks, the hot, glowing matter that spirals into black holes or similar objects. The behavior of matter in these disks could reveal subtle differences between black holes and dark energy stars. For instance, the absence of a true event horizon in dark energy stars might allow some of the infalling matter to escape, producing unique light patterns that telescopes could detect. Gravitational waves offer another potential pathway for discovery. These ripples in spacetime are generated by massive objects in motion, such as merging black holes. If dark energy stars exist, their mergers might produce gravitational wave signatures that differ from those of black holes. Detecting these differences would require highly sensitive instruments, but ongoing advancements in gravitational wave astronomy make this a plausible goal for the near future. Despite the challenges, the search for dark energy stars is a testament to the power of human curiosity and ingenuity. It represents a bold attempt to confront the unknown and push the boundaries of our knowledge. Whether these objects turn out to be real or remain a theoretical construct, their study enriches our understanding of the universe and inspires new questions about its fundamental nature. The possibility that dark energy stars could replace black holes in our cosmic model is a paradigm shift of the highest order. It forces us to reevaluate decades of astrophysical research and consider alternative explanations for some of the universe's most mysterious phenomena. But this is not a story of rejection or contradiction, it is one of refinement and evolution. Science thrives on the continuous interplay between theory and observation, and the hypothesis of dark energy stars exemplifies this dynamic process. As we move forward, collaboration between theorists, observers, and experimentalists will be essential. By combining theoretical insights with cutting-edge observations and experiments, we can begin to unravel the mysteries of dark energy stars and their place in the cosmos. This journey will not only deepen our understanding of these hypothetical objects, but also illuminate broader questions about the nature of reality and our place within it. Ultimately, the exploration of dark energy stars is a reminder of the vastness and complexity of the universe. It challenges us to think beyond the limits of our current knowledge and embrace the unknown with curiosity and determination. Whether we find these objects or discover something even more unexpected, the quest itself is a testament to the unyielding human spirit, a drive to understand the cosmos and uncover the secrets that lie beyond the stars. As we continue to explore the theoretical underpinnings of dark energy stars, it is important to emphasize how they could reshape the way we approach some of the universe's most fundamental questions. In many ways, the very concept of dark energy stars challenges the core principles of astrophysics, inviting scientists to venture into uncharted territory. But what exactly would these objects look like, and how would they behave under extreme conditions? One of the defining characteristics of dark energy stars is their composition. Unlike traditional black holes, which are thought to be formed from collapsing stars or supermassive remnants, dark energy stars would have a unique internal structure. Instead of containing a singularity, an infinitely dense point that current physics cannot fully describe, these stars would be composed of dark energy, a mysterious substance that appears to work against the gravitational pull of matter on a cosmic scale. The nature of dark energy itself remains elusive, but its effects are clear. Dark energy is responsible for the accelerated expansion of the universe, and it is believed to make up around 68% of the universe's total energy content. Its influence is felt throughout the cosmos, counteracting the attractive force of gravity and driving galaxies apart at an ever-increasing rate. But what if dark energy could condense into a stable, localized form, giving rise to a new type of stellar object? In this hypothesis, dark energy would serve as the stabilizing force within the star, preventing it from collapsing in on itself under the influence of gravity. This could create a structure that behaves in many ways like a traditional star, but with fundamental differences in its internal dynamics. Instead of a dense core surrounded by a plasma envelope, a dark energy star might have a central region filled with dark energy, surrounded by a shell of normal matter, possibly similar to a neutron star in structure. One key feature of dark energy stars would be their ability to counteract gravitational collapse. In a traditional star, gravity plays the dominant role in shaping its structure. The inward pull of gravity is balanced by the outward pressure generated by the star's internal fusion reactions. When the fusion process ceases, gravity wins out, leading to the formation of a black hole. However, in the case of dark energy stars, the presence of dark energy could counterbalance the force of gravity in such a way that the star would not collapse into a singularity. This balance between gravity and dark energy could prevent the formation of a traditional event horizon, the point beyond which nothing can escape the black hole's grasp. Instead, the dark energy star might have a boundary that is not a hard edge but rather a gradual transition, where the influence of dark energy becomes more pronounced. This would fundamentally alter our understanding of how matter behaves under extreme conditions and could explain why black holes have always been so elusive in terms of direct observation. If dark energy stars exist, they could potentially solve several long-standing mysteries related to the behavior of black holes. For instance, one of the most puzzling aspects of black holes is their supposed lack of information. The information paradox arises because, according to current theories, anything that falls into a black hole is lost forever, seemingly violating the principle of quantum mechanics, which states that information cannot be destroyed. Dark energy stars, however, could provide a resolution to this paradox. Because dark energy stars would not have a singularity, the information contained within matter that falls toward them might not be irretrievably lost. Instead, it could be preserved in the outer regions of the star, where dark energy interacts with the surrounding matter in complex ways. This could open the door to new ways of thinking about information in the universe and challenge our understanding of what it means for something to be lost. Furthermore, dark energy stars could offer new insights into the behavior of light and radiation in extreme environments. Black holes, by definition, do not emit light in any form, as their gravitational pull is too strong to allow anything, radiation included, to escape once it crosses the event horizon. However, dark energy stars might allow certain forms of radiation to escape, albeit in altered forms. For example, rather than being entirely consumed by the object, light might be redirected, bent, or transformed by the star's unique internal dynamics. This would lead to new observational signatures that scientists could detect, offering valuable clues about the true nature of dark energy. The discovery of such exotic objects would also have profound implications for the study of cosmology. Dark energy stars could potentially offer new ways of investigating the expansion of the universe. Since dark energy is thought to be responsible for the accelerated expansion, understanding how dark energy behaves in the context of individual objects could help scientists refine their models of cosmic growth. This could lead to new insights into the fate of the universe itself, including its ultimate destiny, whether it will continue expanding forever, eventually slowing down, or perhaps experience some form of contraction or even collapse. As we look toward the future, one of the most promising tools for detecting dark energy stars is the growing field of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the movement of massive objects, such as merging black holes or neutron stars. These waves carry vital information about the objects that generate them, and advanced detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, have already provided groundbreaking insights into the nature of the universe. Dark energy stars, if they exist, could produce unique gravitational wave signatures that differ from those generated by black holes or neutron stars. For instance, the merger of two dark energy stars might produce a distinct pattern of gravitational waves, with different frequencies, amplitudes, or durations compared to traditional black hole mergers. Detecting these differences could allow scientists to confirm the existence of dark energy stars and provide a wealth of new data about the nature of dark energy itself. Another avenue for exploring dark energy stars is through the observation of high-energy particles. The accretion disks around black holes often emit powerful jets of particles that travel at relativistic speeds. Dark energy stars could potentially produce similar, though distinct, radiation signatures. For example, the energy emitted by dark energy stars could be influenced by the interaction between dark energy and matter, leading to unique patterns of radiation that might be detectable using space-based telescopes or other observatories. The search for dark energy stars also raises interesting questions about the role of these objects in the larger structure of the universe. If dark energy stars are indeed real, they could play a crucial role in the formation and evolution of galaxies. These stars could act as the dark counterparts to the more familiar luminous stars, influencing the dynamics of galaxy formation and evolution. Just as black holes are thought to reside at the centers of most galaxies, dark energy stars might exert a similar influence, shaping the behavior of the galaxies in which they reside. As research continues and new data is gathered, scientists may be able to detect these mysterious objects directly or indirectly, confirming or disproving the dark energy star hypothesis. Whether or not dark energy stars turn out to be a viable alternative to black holes, their study will undoubtedly yield valuable insights into the nature of the universe and the forces that govern it. As we push the boundaries of our knowledge, it is clear that the universe still holds many secrets waiting to be uncovered, and the concept of dark energy stars is just one of many exciting possibilities that could reshape our understanding of reality itself. As we continue to dive deeper into the possibilities of dark energy stars, it becomes clear that this hypothesis touches on some of the most profound questions in physics, cosmology, and our understanding of the universe. To think of stars not just as massive, burning balls of gas but as objects filled with the enigmatic substance of dark energy challenges everything we know about stellar life cycles, gravity, and the fundamental laws of nature. One of the most fascinating aspects of dark energy stars is their potential relationship with the concept of cosmic inflation. Inflation refers to a period in the very early universe when it expanded exponentially, faster than the speed of light. This process is thought to have been driven by some form of energy similar to what we now call dark energy, which exerted a repulsive force that stretched the fabric of spacetime itself. Dark energy stars could potentially provide us with a window into this distant past, offering clues about the connection between the forces that drove inflation and the forces shaping the present-day universe. In fact, some researchers speculate that dark energy stars could be remnants of this early period in the universe's history, providing a bridge between the moment of creation and the current structure of the cosmos. Just as the first stars and galaxies played a crucial role in the evolution of the universe, dark energy stars could act as unique objects that help us understand the interplay between matter, dark energy, and the expansion of the universe. Another intriguing aspect of dark energy stars is their potential role in the formation of large-scale cosmic structures. In a sense, these stars could be the hidden architects of the universe, influencing the distribution of matter and energy on the grandest scales. The gravitational influence of dark energy stars, while subtle, could shape the behavior of galaxy clusters, the growth of supermassive black holes, and even the expansion rate of the universe itself. If dark energy stars exist, they might help to explain some of the mysterious phenomena observed in the cosmic web, the vast network of interconnected galaxies and dark matter that spans the entire universe. The idea of dark energy stars also raises profound philosophical questions. In the study of cosmology, we often grapple with the concept of the observable universe, which is the portion of the cosmos that we can see and study with our current technology. But what if dark energy stars are located beyond the reach of our most powerful telescopes, hidden behind the veil of space itself? These objects could represent a form of cosmic, dark matter that influences the universe without ever being directly observed. If such stars exist, it would challenge our very notion of reality and the limits of human knowledge, forcing us to reconsider what it means to see and understand the universe. Moreover, the discovery of dark energy stars could provide us with a new framework for understanding the ultimate fate of the universe. As we discussed earlier, dark energy is responsible for the accelerated expansion of the cosmos, driving galaxies apart at an ever-increasing rate. Some theories suggest that, if the influence of dark energy continues to grow, the universe may eventually experience a big freeze, where galaxies, stars, and even atoms drift farther and farther apart, eventually reaching a state of absolute emptiness. But dark energy stars might offer an alternative scenario, one in which these objects play a role in halting or altering the expansion of the universe. If dark energy stars exist and are stable, their presence could provide a mechanism for balancing the forces of expansion and contraction on a cosmic scale. This could change our understanding of the universe's future, suggesting that instead of an endless, cold void, the cosmos might find a new kind of equilibrium, one in which dark energy plays a more complex and dynamic role than we ever imagined. Theoretical physicists also speculate that dark energy stars could provide a new way of looking at the relationship between gravity and quantum mechanics, two of the most fundamental forces in the universe. These two forces, while well understood in many respects, have never been fully reconciled in a single theory of quantum gravity. Dark energy stars might offer an unexpected solution to this long-standing problem, providing a real-world laboratory where quantum effects and gravitational forces can interact in ways that we can study and model. For example, if dark energy stars were to exhibit unusual quantum behaviors, such as fluctuations in their energy levels or interactions with particles in ways that defy our current understanding of physics, it could lead to a breakthrough in our understanding of quantum field theory. This, in turn, might pave the way for a deeper understanding of the quantum nature of spacetime itself, helping to bridge the gap between the macroscopic and microscopic worlds. Moreover, dark energy stars could open up new frontiers in astrophysical research, offering a new class of objects that could be studied with advanced tools like gravitational wave detectors, X-ray telescopes, and particle detectors. While the search for dark energy stars remains theoretical, the tools available to astronomers and physicists are becoming increasingly sophisticated, enabling us to probe deeper into the mysteries of the universe. Instruments like the James Webb Space Telescope, which is poised to deliver unprecedented views of distant galaxies and stellar objects, could provide critical insights into the nature of dark energy stars and other exotic phenomena. Furthermore, as our understanding of dark energy continues to evolve, it's possible that we might begin to detect indirect evidence of dark energy stars in the way that we have detected other previously hypothetical objects, like dark matter and black holes. For instance, the gravitational effects of dark energy stars could leave subtle imprints on the cosmic microwave background (CMB) radiation, the faint afterglow of the Big Bang that permeates the entire universe. Studying these imprints could give us the first direct evidence of dark energy stars, providing a glimpse into a hidden sector of the cosmos that we have only begun to explore. Dark energy stars might also serve as crucial pieces in the puzzle of galaxy formation. As mentioned earlier, black holes are often found at the centers of galaxies, where they exert enormous gravitational pull on their surroundings. If dark energy stars exist, they could represent a different kind of central object in galaxies, one that interacts with matter and energy in fundamentally different ways than black holes. Instead of devouring matter in a relentless cycle, dark energy stars could influence their galaxies through their unique energy fields, guiding the growth and evolution of stars and other cosmic structures. In some scenarios, dark energy stars could even act as a source of dark matter, providing a link between the mysterious substance that makes up a large portion of the universe's mass and the more familiar forms of matter that we observe. The interaction between dark energy, dark matter, and normal matter could reveal new insights into the underlying structure of the universe, potentially leading to a unified theory that explains the relationship between all three. As we look ahead to the future of cosmological research, one thing is certain: the concept of dark energy stars will continue to capture the imagination of scientists and laypeople alike. Whether they are ultimately proven to exist or remain a tantalizing possibility, these hypothetical objects offer us a new way of thinking about the universe and our place within it. They challenge us to reconsider the nature of stars, black holes, and even the fabric of spacetime itself. In doing so, they open up a new frontier of exploration that promises to deepen our understanding of the cosmos in ways that we can hardly imagine. The search for dark energy stars, if it proves fruitful, may one day lead to new insights that not only reshape the field of astrophysics, but also redefine our understanding of the very fabric of reality. The mysteries of dark energy and dark matter are far from being solved, but dark energy stars offer a compelling glimpse into the future of cosmology. Whether we will find them in our lifetime or not, one thing is certain: they will continue to spark curiosity, creativity, and new ways of thinking about the universe we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.